Hello everyone, welcome to my YouTube channel. Today we are diving into one of the most elegant algorithms in graph theory. This is a powerful technique used to find the minimum spanning tree of a graph. First, let's understand what Prim's algorithm is all about and why it is so important. Prim's algorithm is a greedy algorithm designed to find the minimum spanning tree or MST of a weighted, connected and undirected graph. Now, what is a spanning tree? A spanning tree is basically a subgraph that includes all vertices of the original graph and forms a tree structure, meaning it is connected with no cycles. But what makes it minimum spanning tree? Among all possible spanning trees, the MST has the smallest total edge weight. That is the key, minimum total weight. So where do we use in real life? First, in network design. Imagine you need to lay cables or pipes connecting between multiple cities. You want to connect all of them with the minimum total cost. That's exactly what Prim's algorithm solves. It is also used in circuit design to connect components efficiently in transportation networks for building roads with minimum distance, and even in cluster analysis for finding related data points in machine learning. Pretty useful, right? Now let's understand how Prim's algorithm actually works. The key principle is beautifully simple. Prim's algorithm builds the MST by growing a single tree starting from any vertex you choose. At each step, we add the minimum weight edge that connects a vertex already in our tree to a vertex that is still outside the tree. That's it. Always pick the cheapest connection to expand your tree. Let me break down step by step process. First step, start with any vertex and mark it as visited. It doesn't matter which one you choose, the algorithm will give you the same total weight regardless. Second step, look at all edges that connect your visited vertices to unvisited vertices and select the edge with the minimum weight. Third step is add that selected edge and its connecting vertex to your MST. Next step is repeat second step and third step until all vertices are included in your tree. In terms of efficiency, when implemented with a priority queue, Prim's algorithm runs in order E log V time, where E is number of edges and V is the number of vertices. That's pretty efficient for most practical applications. Let's talk about the heart of Prim's algorithm. The greedy choice of selection minimum weight edges. At each iteration, Prim's algorithm makes what we call a locally optimal choice. It picks the minimum weight edge that expands the tree. And here is the beautiful part. This greedy approach actually guarantees a globally optimal solution. Why does this work? There are several reasons. First, we always maintain a valid tree structure with no cycles. Second, we connect all vertices, giving us the spanning property. Third, since each edge we add has the minimum weight among all available options, and that moment we ensure the total weight is minimized. From an implementation perspective, we typically use three key data structures: a priority queue, a visitor set, and edge list. A priority queue to efficiently find the minimum weight edge in logarithmic time, a visited set to track which vertices are already in our MSD, and an edge list is to store the actual edges that form our minimum spanning tree. This combination allows to us implement the algorithm efficiently. Alright, theory is great, but let's see the algorithm in action with concrete example. Here we have a weighted graph with 5 vertices labeled A through E. Look at all these connections and their weights. We have weight A to B with weight 4, A to D with weight 2, B to C with weight 5, B to E with weight 3, D to E with weight 7, and E to C with weight 6. Our goal is to find the minimum spanning trees starting from vertex A. Remember, we could start from any vertex, but let's choose A for this example. Let's see how Prim's algorithm builds a MST step by step. First step, we start by selecting vertex A and marking it as visited. You can see vertex A is now highlighted in green. Now from vertex A, what edges can we consider? We can go to B with weight 4, or we can go to D with weight 2. According to our algorithm, we need to select the minimum weight edge. Between 4 and 2, clearly 2 is smaller. So we will select edge A to D with weight 2 as our first edge to add the MSD. At this point, our visited set contains just A. We have 2 available edges to choose from, and we have selected A to D. Our MSD is still empty because we have not officially added the edge yet, and our total weight is still 0. Let's move to the next step. Now we add edge A to D to our minimum spanning tree. You can see both vertices A and D are now highlighted in green, and the edge between them is also highlighted. Our visited set now contains vertices A and D. From these two vertices, what edges can we explore? From A, we can still go to B with weight 4. From D, we can go to E with weight 7. So our available edges are A to B with weight 4 and D to E with weight 7. Which one has minimum weight? That's A to B with weight 4. Now our MST contains one edge, A to D, and our total weight is 2. See how we are always picking the smallest available edge that spans our tree. That is greedy choice in our action. Step 3, we add edge A to B, our minimum spanning tree. Now vertices A, D, and B are in our tree. That's shown in green. Let's look at what edges we can now explore. Our visited vertices are A, D, and B. From B, we can reach C with weight 5, or we can reach E with weight 3 from D, we can still reach E with weight 7. So our available edges are B to C with weight 5, B to E with weight 3 and D to E with weight 7. What is the minimum? B to E with weight 3. Our MST now contains two edges, A to D and A to B. Total weight so far is 2 plus 4, which equals 6. We are making great progress. Notice how the tree is growing outward, always taking the cheapest path to expand. Next step, step 4. We add H, B to E to our MST. Now we have vertices A, D, B and E all in our tree. Here is where it gets interesting. Let's examine our available edges carefully. From B, we can reach C with weight 5. From E, we can also reach C with weight 6. What about D to E with weight 7? Here is important point. D to E with create a cycle because both D and E are already in our tree. Remember, a tree cannot have cycles. So we skip any edges that would connect two vertices already in our visited state. So our real available edges are B to C with weight 5 and E to C with weight 6. The minimum is B to C with weight 5. So that's what we'll selected next. Our MST now has three edges, A to D, A to B and B to E with a total weight of 9. Just one more vertex to add, vertex C. And here we have it, our complete minimum spanning tree. We have added the final edge B to C with weight 5. Now all 5 vertices are connected, shown in green, and we have our complete MST. Let's review what we have built. Our MST consists of 4 edges, A to D with weight 2, A to B with weight 4, B to E with weight 3 and B to C with weight 5. The total weight is 2 plus 4 plus 3 plus 5, which equals 14. This is the minimum visible total weight to connect all 5 vertices. Notice something important. We have 5 vertices and 4 edges, and this follows the tree property where a tree with n vertices has exactly n minus 1 edges. And here is guarantee. There is no other way to connect these all vertices with a lower total weight than 14. Prim's algorithm has found the optimal solution. Let's wrap up with a quick summary of everything we have learned today. Prim's algorithm efficiently finds the minimum spanning tree of a weighted graph. It uses a greedy approach, always selecting the minimum weight edge that expands the current tree. The algorithm guarantees an optimal solution. You can't do better than MST it finds. With a priority queue implementation, it runs order E log V time, which is quite efficient. What are the advantages? Well, it is simple to understand and implement. It works particularly well for dense graphs when you have many edges. You can start from any vertex and still get the same optimal total weight. And most importantly, it always produces optimal results. Now, you might have heard of Kruskal's algorithm. That's another algorithm for finding MSTs. So, what's the difference? Prim's algorithm grows a single tree from a starting vertex, adding one vertex at a time. On the other hand, Kruskal algorithm sorts all edges and builds the forest by adding minimum weight edges globally, eventually merging into a single tree. Both algorithms produce an MST with the same total weight. They are both correct. The choice between them often depends on the graph structure and implementation preferences. That is Prim's algorithm. I hope this explanation clear and helpful for you. So thank you for watching. I will see you in the next video. Bye.